Firstly up, I'll apologise for a bit of AV. We might have some challenges partway through, but thank you for your patience. So, hi folks, welcome to DAT442. If you're not here to learn about Aurora and resilience, you're in the wrong place. My name's Tim. Shortly, excuse me, I'll be joined by Mark, and we're going to talk today about Aurora and how to bring resilience to your applications using Aurora. So who here, show of hands please, runs a database in production? Most people, cool. Who here, because you're at reInvent, you're not at work right now, who here feels a little bit uneasy about running a database in production? Lots of hands actually, right? So you got a pager in your pocket for that kind of thing? So I'm happy that you're here. We're going to learn today. There's a whole bunch of choices we can make about making any system more resilient, and Aurora is no different. Right, so what we're going to do, first we're going to define resilience so we know we're talking about the same thing. Right, so resilience is, technical definition, the ability of a workload to recover from disruption, or for infrastructure to recover from disruption, to dynamically acquire resources, to meet some demand, and to mitigate disruptions caused by misconfiguration or something like that, right? So it's not just about when something crashes. It's not just about when a server catches fire. It's got performance and a whole bunch of other things in it too. And it's really got two pillars underneath it. It has availability and disaster recovery. So availability, that's a proportion of time that a workload is available for use. So this is usually a historical time measure. We might say it's been 5 nines availability for the past 1 year or something like that. That's when we talk about availability. The other one is disaster recovery, or DR. So normally when we talk about DR, this is the techniques you use to recover your workload when something goes wrong. Maybe there was a volcano, something like that, or some human threat. Here we use recovery time objective, RTO, as one of the measures that we talk about. So that's the maximum amount of time between one single event and the resumption of service. That's your return to operations time. And then there's the recovery point objective, the RPO, which is a maximum amount of data, normally measured as an amount of time, that we can afford to lose, maybe due to asynchronous replication or something like that. And you might want your RPO to be 0. That's a valid value as well. Okay, so that's the level set. So now we're just a bit of an agenda. Next, we're going to talk about Aurora Postgres, which I'll call APG, and Aurora MySQL, AMS. I have to say that word about 10,000 times, so apologies for the acronyms there. Now, they're both very similar, so a lot of the features that they support are similar, so I will talk about them together with respect to resiliency. And then about halfway through, Mark will pick up and he will talk about the same set of questions that we're going to ask ourselves about DR and HA. He's going to answer them again, but from the point of view of Aurora DSQL. So keep your bearings. First part, Aurora MySQL and Postgres. Second part, DSQL. Okay, so first, if you don't know anything about Aurora APG and AMS, what are these things? So they're relational database services that combine the speed and availability of a high-end commercial database with the simplicity and cost-effectiveness of the cloud and open source. So APG and AMS are fully compatible with Postgres and MySQL open source engines, and that allows your existing applications and tools to run without modification. So today we're going to go into some questions, like 5 questions we're going to ask ourselves. But if you want to ask your own questions, there's a chalk talk, DAT424 on Thursday as well, that you're more than welcome to come along to and hit me up. All right, so question 1 we're going to ask ourselves about HA and DR. What if my database node fails? So if you're in self-managed, this is self-managed, little tag up in the corner there we can see. So if you're just starting out with self-managed, you might have a system that looks like this. You've got one node. It's got your database engine, it's got your storage inside the same node, and there's only one of them, right? So that means that all of your storage and execution work happens in there. You might back that up with some third-party tool. You might send your backups to S3. When you do the backup, we might need to do some kind of quiesce thing there, so that's going to slow down your performance, maybe give you some bumps in availability. That's not great. Because that's really difficult, we probably don't do that backup very often. Maybe we do it once a day. So that means that your RPO is something like 24 hours. That's not so great. So then if that node goes down, it means that your storage and your engine has gone down, right? So that's not great for your availability, and it's maybe not great for your durability either. So your RTO could be many hours. Not a great situation. So let's look inside Aurora and look at the durability story first, the RPO part. So you can start with a single database cluster over there on the left-hand side there and one availability zone, single instance, and we're going to use this empty box at the bottom here. We'll fill it in as we go through today. This is Aurora Storage. Grover is its code name. This is where all the magic happens with Aurora for AMS and APG. So Aurora Storage is a multi-tenant storage fleet. We've got storage nodes, they're the big pink boxes, they're spread across 3 AZs. They're multi-tenant, so they've got some other customers' data inside there as well. They're the little colourful boxes. Sorry about the bad graphics. All right. And so what we're doing is every write that you make through from your engine, we're going to make 6 copies of that write across 3 availability zones. You're only going to pay for one of those copies. What that means is that we can lose a whole availability zone worth of storage nodes and one more of them, and we still don't have any durability problems, right? So it's a really strong durability story out of the box with Aurora. You did nothing to configure this as you're getting 6 copies across 3 AZs. All right, so your RPO is 0. There's no asynchronous replication going on here. So just by using Aurora, MySQL and Postgres out of the box, you get this. So we'll dig a little bit deeper in this area. So what is this data that we're storing in here? So a traditional database writes a log record of what it's doing, then it writes the pages, and then it might come back and checkpoint them. It has to do this in case it gets interrupted, right? What Aurora's doing is it's writing just those log records. It's not writing pages, never writes pages to disk. It only ever writes log records. The storage understands how to apply those log records and turn them into database pages again, which we need when we need to save some space or we need to satisfy some reads. So if you think about it, what that means is Aurora has this whole timeline of what's happened inside the database. Every single commit that's happened into the database, we have it there in sequence. So that's how we can implement some of these features we'll talk about. All right, so first one of those features is backup and restore. So on the left there, you've got your production cluster. Your database is writing down, so I've got some coloured lines there, those boxes. They are the different database pages and their log record lineage, right? So what we're doing is the storage engine, not the head node, is continuously backing up all that data to S3. So the first key point there is your head node's not doing it, so it can't possibly impact performance of your head node. There can't be any quiescing or anything. This is continuous. It's happening all the time. So what this allows you to do then is to do a point-in-time restore from anywhere from the earliest restorable time, which can be up to 35 days, configurable in your retention window, up to the latest restorable time, which is about 5 minutes ago for a busy database. Any point in time there we can choose. So let's do one of those restores. Let's choose time equals 7, because I'm unimaginative, to do this restore. What's going to happen is those storage servers are going to pull that storage data back from S3. We're going to apply our internal log records to catch you up to exactly that point in time. And then we're going to start up an engine, and the engine's going to do its normal transaction recovery logic, so it's its logical level to handle interrupted transactions and things like that, right? So again, to answer the question, the second part of your job is really easy because all of this comes out of the box. You didn't have to do anything to support PITR. Grover's doing for you underneath. All right. So that's data, but what about database instance availability? So in your most basic configuration can look like this. You've got one instance. If it fails, then we can make another one, but it'll take 10 or 15 minutes. So what you can do is you can bring up another instance here. We'll call it a standby. Aurora will keep it in sync as well. So remember, they're sharing the same storage, and every transaction that's happening, we're telling the other guy about it as well. So now you've got a replica. So whenever something needs to fail over, we'll make them the same size. Whenever something needs to fail over, then the other one can take over really quickly within just a few seconds. And because they're the same size, they can shoulder the same amount of load, right? This one becomes a primary. So this gives us an RPO of 0 because they're shared storage. They're not replicating storage, right? We're not worried about asynchronous commits or anything like that. When you fail over, your RTO is typically around 30 seconds. So by doing this is one of those patterns to get what we call the multi-AZ availability pattern. Really increase your availability. Okay. So what about performance is the next question. So performance can fluctuate, right? Your application can push harder on you, then it can push softer on you, and you might be wasting money instead. So we want to be resilient to these performance level changes too. So open source, you've broadly got 2 ways to deal with this, right? So you can scale up an instance. Probably that means buying some hardware and doing some migrations. That's a bit hard. Or we can do some scale out, which means in the application layer, you would have to be aware and divide your database into pieces, and your application has to know which piece to go and talk to. That's really difficult for consistency. You have to deal with it as well. And noisy neighbours is tricky to deal with too in this situation. So back to AMS and APG, what can we do about this? Well, we can add that replica that we had before. We don't just need to add it for availability purposes. We can add it for performance purposes too, because we can just send reads to that other replica, right? It's going to see stale data up to that asynchronous lag, 100 milliseconds or something, maybe like that, right? But it's completely offloaded. It's not going to have any impact on performance on the writer. Now, if you've got another workload, maybe like some kind of analytics job or something, then you can run that on another replica. Then all the resources on that replica are isolated for that application. Its buffer pool being the most important one for performance. So this is really important for resiliency against performance changes when you can separate out your noisy neighbours. So you can add up to 15 of these replicas. So you can be quite fine-grained here. Each of them, if you're really big, they could be 48x largest. That is 1.5 terabytes of memory. That's a big system, 15 of them, right? Now, I haven't talked about anything to do with storage scaling yet, and that's because you don't have to worry about it. So the storage is scaling in capacity automatically, and it's also scaling in performance automatically. There's no performance provisioning in AMS or APG at all. Okay, now instance scaling. So we have this instance off to the side there. It's an R8G, latest Graviton 4. It's a 16x large. Pretty big box, not the biggest one we make, right? So we can add the same sized ones, good for failover like we talked about. We can add different sized ones, 8x cells, 4x cells. We can add this db.serverless thing too, which we'll talk about some more. That's an elastic instance that grows and shrinks all the way from 0 all the way up to 256 Aurora capacity units. When we do have a lot of instances like this, we have to decide which order we want to fail over to them. There's no good me trying to fail over to one of those 8x cells because it'll be too small to deal with the load that I have. So I need to define these failover tiers, we call them. The tier with the lowest number, tier 0 in this case, that's where we'll fail over to first. That serverless instance, we'll talk about a little bit more, can expand and contract, so you're resilient to going up when you have a spike in workload, and then you're not going to get stuck there paying a bunch of money. It's going to scale back down again. Okay, so with all these instances, that's all good, but my application has to connect to them somehow, right? And that can be a bit pain to know which one is the writer. I need to talk to that one if I need to send transactions that have writes in them, like updates. How do I do it? And I don't want to have so many of these connections either. I don't want to have lots of idle connections. That's not great for performance, not great for cost. So I don't know which connection is going to go where, and it's going to have high overhead even if I can work it out. So that's probably not a great situation for self-managed. So I can use two techniques here, pooling and limits. So we can limit connection count per DB instance. The big one should get more connections than a small one maybe. Per type, I can avoid reconnections. This is all pretty standard. There's no special Aurora here. If you've done databases for a while, this should look pretty familiar. Some of this stuff is provided for you by the driver frameworks that you already use, if you're using Spring maybe and JDBC and some other things, right? But they tend to fall down with clustered databases like what we're using here because they don't understand what's going on. So the first thing we're going to talk about is endpoints. With Aurora, we have two endpoints, generally speaking. You have a writer endpoint, which will always point to the node that is the writer right now. And when that changes, we will point it somewhere else. So you can always just send your writes to the writer. Then we have a reader endpoint, which points to the pool of, remember, because there could be 15 of them, the pool of instances that can accept reads using DNS round robin. So because it's pool, that lets you just do some coarse load balancing there as well. So when we need to fail over, then we just repoint the writer endpoint. That can happen really quickly just with a DNS lookup and a reconnection. Your application already has to handle this reconnection anyway for other errors. So this way we can turn over in basically what the DNS time is, 35 seconds or something like that. Okay? For further flexibility, you can create a custom endpoint if you want to just group together a few endpoints and call them the analytics endpoint or something. You can do that too. It's up to you. All right? So further to this, though, we have this thing called AWS Advanced Wrapper Drivers, right? So this is when we talk about availability, not just performance of that connection kind of question. So each of your applications pieces of code has to have specific reconnection code inside it to deal with these errors. Right? It has to recognize that this is a retriable error, it has to deal with that. It has to do this fast enough because this is availability time. It's a bit of a problem, right? So Aurora gives us two extra tools here. We've got wrapper drivers and we've got RDS proxy. So the wrapper drivers, they've got intimate knowledge of what's going on inside a cluster. They know which ones are the readers and the writers at this point in time. And so they can handle failover much more quickly. They're built by wrapping around your existing platform driver, like JDBC in this case, but we have them for ODBC, Node.js, Python, a bunch of other ones, right? So if you've already qualified your platform driver, we're not going to change it. We're just going to wrap it with some plugins. One of those plugins is called Enhanced Failover. Another one's read-write splitting, blue-green, which we'll talk about, and a few more. So if you're not using these drivers, we really encourage you to go and do that. Great for a whole bunch of reasons. What this will do, this will reduce your failover time down to about 6 seconds as well. Okay, so if you're interested, there's a QR code for the GitHub project there, where all of these are open source. We're not doing anything kind of secret squirrel here that you can not do yourself. We're just doing it for you. Right, so that was all in one region, but what about multi-region? So what about if a whole region fails, right? Well, that's a problem. Maybe if my business needs to continue when that region's down, or if even if that region didn't fail, but if it's cut off from the network, which is maybe even a more likely failure scenario. So what we've got here, what we'd like to have is a copy in another region, and we'd like to be as up-to-date as possible. We'd like it to not cost us very much money, and we'd like to be able to use that copy for other things. If you're self-managing, this is pretty hard. So with Aurora, we have Aurora Global Database for AMS and APG. So this is where you can add up to 10, but I can only draw one here because my slide's not big enough, 10 secondary regions. So on the left, region A, we have the same picture we've been talking about for 15 minutes now, right? Some replicas, some storage. When we add another region into this thing, we internally in Aurora, we spin up a replication server, replication agent. We handle this asynchronous physical replication between them. So notice how, so your head nodes are not involved in this at all. This is not logical replication. You're not having to pay for the performance tax of binlog with MySQL and things like that. We're doing it all underneath, okay? So that means your application doesn't even know that this is happening. So you can have up to these 10 global secondaries without even knowing about it, right? So we write some of those log records, those colourful boxes I'm so good at drawing. They also get replicated over to the other side on storage in region B. You notice how there's no head nodes in region B at the moment in my picture. There's only storage. So in this particular configuration right now, this is good for keeping your data available, durable, but it's not really good for availability, right? We haven't got our workload able to run over there. Your RPO, the lag, because this is asynchronous between the region A and region B, it's typically about a second. It depends on your choice of region pairs. I can't do anything about the speed of light, I'm afraid. So if they're far away, it's going to be a little bit slower. All right. And then if you wanted to, what we could do is we could add some other instances over to the secondary region as well. Now I've drawn a symmetrical configuration here, but this does not need to be symmetric at all. You can have as many different instances there as you like, and they're read-only nodes. They're replicas, just like we said before, so they can do low latency, local reads. All right, so if you don't test it, then you don't know it's going to work. So what you've got to do, first we have this global endpoint thing, right? So the same question we had before about how do you know which one is the writer that you've got to point at? Well, if we zoom that out to the next level up, the global level, how do you know which region is the primary region at that point in time? Well, that's where this thing called a global endpoint comes in. So if there's some issue in region A, we've got that global endpoint name there, and you're going to trigger a failover first. We'll talk about that some more. That means the writer is going to move over to region B. This is a managed operation. You see that -- allow data loss flag down in the bottom corner there? That's to say that, remember, to try and remind us all that this is asynchronous replication. So anything that was inside that asynchronous replication window has a chance of being lost when we do a forced failover. Okay? So when that's happened, the writer has moved over to the other region. We've got a new primary region now, region B, and the global endpoint is going to be pointed back at that using Route 53 data plane. So that happens as fast as we can make it happen. All right, so this gives you really high write availability across multiple regions. So what if something hasn't failed in global database? We just want to do what's called a switch over. So this is what you do when region A and region B are both healthy, not when one of them's gone bad. So what we want to do is we want to tell region A, you should stop being the primary, and region B, you should start being the primary at this point in time. Now, this is pretty interesting the way we built this to allow it to happen so quickly, so I want to go into it a little bit. So we have this log record stream, right? So we insert this special log record into that stream, a marker log record, and that flows through just like we described before, and the other side sees it. So when the other side sees it, it says, okay, at this instant in log time, not wall clock time, I should become the primary right now. And region A knows that he should stop being the primary at that time. So there's a nice clean handoff. We can get 0 RPO, really low RTO. And I just think it was pretty funky. I wanted to tell you how it worked, right? Okay. So, and then we also know that that'll give us this RTO about 30 seconds and RPO of 0, right? So the final question we're going to ask ourselves is, what about maintenance? So like version upgrades. So remember, we're fully open source compatible, so we have a version. We might have Postgres 16 and we need to get to Postgres 17. Well, how do we do that? We might just have a patch or an OS patch that we need to apply. How do we do these things? They're all upgrades, we call them. So if you're self-managing, then you'd have to take a downtime window, right? You'd have to go and talk to your customers, work out when they would like to have some downtime. You would need to take some snapshots so that you can do some rollback. That might be difficult if you don't have the cool storage like we do. You'd have to coordinate with everybody. You'd have to do compatibility and testing, and lots of it, between your application, between the old database versions, all these other things. Something people often overlook, though, is performance, is that when you do an upgrade, probably even if you just do any old restart, your performance is probably going to drop because you've just restarted your engine and lost your buffer pool, right? So performance testing's got to be part of your upgrade compatibility as well, if you're self-managing. So whether you're in APG or AMS, because we're fully open source compatible, we can't ignore this, right? We must maintain a strong security posture. So we provide a fully managed and automated, if you like, minor version and patch upgrade experience. So we can see here in the console, we got some maintenance actions there. There's an upgrade available for this database cluster. So we do rolling operating system upgrades now. That we didn't used to do that. That means we have an increased availability. You define a maintenance window. If you don't want to define it, we'll define it for you. That says that this system will receive any automated maintenance within this window of time, if you like. Okay. You'll get maintenance here and in the AWS Health Dashboard. And this is all able to be automated if you like. It's opt-in. We, of course, strongly recommend that you opt in because then you don't have to think about it anymore and we'll deal with it. All right. Now, a new thing for us here, AWS Organizations Upgrade Rollout Policy. Bit of a mouthful. But what that means is we had a good story for a while about how to automate the lifecycle of one DB cluster. But I hope that most of you probably don't have one DB cluster. You've probably got tons of them. You've got a fleet of them, and you want to manage them as development and QA and prod or some other mechanism that you've got. But we never really gave you a way to deal with that before. This is where organizations upgrade rollout policy comes in. So on the left, we have a GUI screenshot. On the right, we have the JSON version of the same thing. So what this means is that you set a policy based on tags. So here we have a tag called env. And we say that any resource inside my AWS organization, that might be an account or a DB cluster, that has an env flag value of prod will be upgraded last. And you can see some other ones there. If it has an env value of dev, it'll have to be upgraded first. Go into this some more. And anybody who doesn't have a tag that I recognize, they'll get upgraded second. That's the default at the bottom there. All right. So how does this happen when we actually roll it out? So we built that policy. Now we have to assign it to the resources in our organization. Maybe it's an account or all of the things in the organization. And then what will happen is you can see this. You can see the upgrade order is determined to be second for that resource there. That's really helpful. So first we'll notify you. Then we'll wait for the maintenance window of the resources in the first wave. And then we'll upgrade them. And then we'll let them sit there and cook for a little while until the maintenance window for the resources in the second wave comes along, and then we'll upgrade them, let them sit for a while in the final wave. Right? So we're not actually blocking from the first one to the second one, but we're waiting. And if you've found some issue in that time in there, you'll know how long that window is. It's different for different resources. Then you'll be able to remove the tag or turn off AMVU at that point in time to stop the progression of upgrades. All right. In-place upgrades. If we're doing major upgrades, they're incompatible by definition with open source. So we can upgrade in place. We can do this first by creating a clone of the database cluster, which happens really fast and doesn't cost anything. We don't charge you for the storage other than for when you make changes to the storage. Then we can practice on the clone. We can upgrade the clone. We can test the clone with an application. Then when we're happy with that, we said, great, okay, throw the clone away and upgrade in production. That's one way to do an in-place major version upgrade. Pretty straightforward. All right. A more flexible way, if we can do it, is to use what we call blue-green. So here I've got my production situation here. I've got a couple replicas, an endpoint, and I'm going to use blue-green to do a major upgrade. I don't have to do just for a major upgrade. I can do schema change, static parameter change, anything like that. Blue-green means I'm going to call my old environment blue, I'm going to make a new environment called green, and I'm going to keep them in sync with logical replication. You're not doing any of this, I'm doing this. We do the upgrade, still in sync with logical replication, you test it. When you're happy, you trigger blue-green switchover. In switchover, I promote the old one to the green one to be the production. The old resource is still there. All the resource names are renamed so that you don't have to go through any of your scripts afterwards and things like that. After the blue-green's happened, it's as if it never happened. Okay, very flexible. And this switchover can complete in as little as a minute. All right. So in case you missed it, this same thing with blue-green, we just announced for global database as well. So here we have our blue configuration, our green configuration across 2 regions in this case. Everything I just described to you for blue-green, exactly the same, except multiple regions. All right, so far we've learned how APG and AMS, out of the box, give you protection, just that storage at the bottom there, against one whole AZ unavailability plus 1. And then we saw how we can add some replicas in here to increase our availability and allow failover to happen. And we can use AWS Advanced Rapid Drivers to smooth that out. Then we learned how global database can be used to provide durability and availability across up to 10 secondary regions, supporting low latency local region reads and simple cluster endpoint management with that global endpoint. And finally, we learned some of the patterns to follow to keep your database cluster up to date. With managed and automated cluster-wide upgrades, fast clones, and blue-green. So now I'm going to hand over to my buddy Mark when he comes, and maybe change some slides, I think, to tackle those same 5 questions again, but from the point of view of DSQL. Thank you.
Okay. Hi, everyone. My name is Mark. Sorry about the unplanned downtime there. For the rest of this talk, we're going to be looking at building resilient applications using Aurora DSQL, which is the newest engine in the Aurora family. Aurora's been around for about 10 years. This is only 6 months old. And DSQL comes from our customers asking us to give them the best of relational. So this is the ability to run complex queries, joins, evolve your schema, the best of distributed database architectures like DynamoDB, where there isn't a single point of failure, where we scale out rather than up. And if that's not all, also the best of serverless services like Lambda, where you're only paying for what you use. We're going to go through all 5 questions again, starting with what if my database node fails. But before we do that, let's take a crash course into the DSQL architecture. On screen, we have self-managed Postgres that you've downloaded from the internet. You're running on an EC2 instance. Our application is connected in. We're exchanging some credentials. And the server is going to fork itself, creating a dedicated Unix process for our connection known as a backend process. We can connect a few times, a bunch more processes. And each of these sessions can run queries that are going to parse, plan, and execute your SQL against local storage. Of course, we can run updates too, sending those to the write-ahead log, which is being used to keep storage up to date. Keep in mind these 3 components because they're going to make a comeback right now. Here's DSQL, our application's connected in, and it's connecting to a component that we call the query processor. This is just like that backend session. We get one of these per connections, and just like we saw in Postgres, we can send SQL select statements that are going to be turned into read queries sent over the network to DSQL storage engine. Meanwhile, writes work a little bit differently. If you run an insert statement putting a new row in the system, that row is going to be buffered in memory on the query processor. If we run an update statement, the QP is going to take that update statement, turn it into a read against local storage to fetch the current version of the row, process that statement to produce a new version of the row, and then again, keep it in memory. And you can keep doing this as you build up your transaction, insert, update, delete, until we call commit. When you call commit, that entire bundle of everything you've asked the database to do is going to be sent over the network to a service called the adjudicator, which is responsible for concurrency control. So this is the part of the DSQL architecture where we're checking for if there are any conflicts happening with other transactions running in the service. For transactions that commit, they are sent to a service called the journal, which is a backbone service of key AWS services like S3. And the journal is responsible for durability. It will replicate our new transaction to at least 2 availability zones. And finally, just like what we saw in traditional Postgres, we're going to be using that journal to keep our storage up to date. If we open another connection, we have another QP. That QP can do reads and writes. But there's nothing in this architecture that says that that QP needs to be running on the same host or even in the same availability zone. DSQL is an active service, which means that any connection can read or write any data at any point in time. So let's talk about availability. What happens if my database node fails? We're connected to that flashing QP in AZ2, and we're doing some fancy joins, and turns out our storage node that we're talking to fails. It explodes. Oh no, what do we do? The answer is you as a customer don't have to do anything because the QP is going to detect that failure. It's going to start to shift traffic over to a healthy replica. Now this replica may be in zone, it may be out of zone. I showed that here on slide. And we're going to continue with only a small increase in latency for any in-flight operations that had to be retried. Meanwhile, DSQL is continuously backing up your data and will detect the loss of this node. DSQL is going to go and take a recent snapshot of your data, create a replacement node in the same zone. That node will come online, it will connect to the journal, it will catch itself up, and then the query processor is going to start to shift traffic back over to its local replica, which is going to give us the best performance because the intra-AZ latency is simply better. But what about that? What about writes? What about that adjudicator sitting over there in AZ1? Well, the reason we have a single adjudicator is because that's going to allow us to do this conflict resolution protocol really quickly without coordinating over the network, but we don't want a single point of failure. And so what DSQL does is it's going to keep standby adjudicators in the other zones. Notice the arrow from the journal, right? These standbys are simply following along with everything that the leader adjudicator is doing. And if anything fails, then within just a few milliseconds, these standby adjudicators are going to run a leadership protocol. One of them is going to become the leader. Hey, it turns out it's R1 and AZ2. And the QP is going to retry any in-flight commits against the leader. There's nothing for your application to do. This just works out of the box. Now, there's a lot more going on with the DSQL architecture than I can show you on the slide. But the good news is that you don't have to know about how any of this works. DSQL is an architecture that's been designed for high availability. There's no single point of failure in DSQL. If you're only spending a few pennies per month on DSQL or running entirely on the free tier, you're getting active out of the box. But of course, DSQL is designed to scale too. And so let's dig into how we do that. First, let's talk a little bit more about that concurrency control protocol. DSQL uses a protocol called optimistic concurrency control, which makes the assumption that transactions seldomly conflict with each other. But what happens when they do? Here we have 2 clients that are trying to update the same row, see where ID equals 1 to a different value. It doesn't actually matter what the value is, but they're going to prepare their transactions, and they're going to race to the adjudicator. It turns out the transaction on the top gets there first. The adjudicator is going to record that transaction in the journal, and our other client is going to be given a Postgres serialization failure error, and it's going to be told to retry. And so when you're building applications on DSQL, this is something that you need to take care of on your application. When you call commit, you need to take care of availability issues, you need to take care of optimistic concurrency control issues, and then just simply retry. This is just a few lines of code, it's a while true loop. And what we recommend that you do is you build little helper functions that you can use throughout your application, or if you're using some kind of framework, then put that into the lowest layer possible. Now, when you design your applications, you want to avoid creating unnecessary conflicts that we don't need to retry. And if you do that, then we're going to be able to commit these 2 transactions at the same time because notice that they're updating different rows. And as you do this more and more and more, you may start to increase the load on the adjudicator, the load on the journal, and so what happens then? Well before you exhaust the adjudicator or the journal's capacity, DSQL is going to notice this increase in utilization and start to shard itself internally. And so if we're updating some records, the QP will automatically know about this internal sharding strategy and direct your commits to the right stack. But of course, we can run transactions that sometimes touch rows from multiple shards. DSQL will handle this automatically for you. We have an optimized implementation of two-phase commit that will ensure your transactions are atomically committed even across multiple shards. Something similar is happening on the storage side, which we won't have time to get into today, but I do want to talk about read scaling. So imagine we're opening a bunch of connections. These connections are all running their selects. They're slamming our single storage host. Load is going up. Latency might go up. But again, well before this becomes a problem, DSQL is going to detect this. And using the same trick that we saw in the availability slide, DSQL will use a recent copy of your data to bring a new node online. That node will catch itself up from the journal, and the query processes will start to automatically load balance across this replica. And we can keep scaling this out without limit. DSQL's doing this automatically on your behalf. And a key reason we're able to do this is because in DSQL, replicas are always strongly consistent. So in order to understand this, let's make a new DSQL cluster. It's completely empty, doesn't have a single row in it. We've made a table, my table, and we are just about to insert our first row into that table. Here we go. It's in the journal. It's being committed to at least 2 availability zones. That means the journal says, I got your data, and we're going to send that commit acknowledgement all the way back to our client. And now our expectation is we can start a new transaction, we can run select star from my table, and we should see our row, right? Because otherwise we'll have an eventually consistent system. Eventually consistent systems are very difficult to reason about. They're very difficult to write correct code against, and that is the reason for our small technical interruption, because we had old slides. Okay. So what we do in DSQL is use a time-based synchronization protocol. And we combine 2 techniques here. The first technique is we use the EC2 time sync service, which gives us a microsecond accurate timestamp using GPS clocks. The second technique is that we use a library that AWS developed called clockbound, which is going to allow for any errors in that measurement. And when we combine these techniques, what we get is a value that is linearizable. That is, it is a timestamp that is guaranteed to be after any commit timestamp that the service has previously given out. And now that we have this transaction start time, this T-start, we include it in our API request to storage. And the job of storage is to identify that it's running behind, to wait, to see the update come off the journal, and then return our rows. So how do I manage connections? Here we have 6 connections to DSQL, and how do we get them? Well, between your application and the query processor is a service known as the session routing layer, and its job is to make sure that connections are always available, that you can get connections quickly, even in the event that many hundreds of thousands of connections flap due to a networking event. This is a very deep and complex service, but at a high level, what's happening is that there is a massive warm pool of these query processes. Again, each of these boxes represents a single process. So our team is maintaining a large fleet of EC2 instances. We're taking on the responsibility of capacity management. And on these instances, we're packing them full of QPs that are ready, they're running, and they're just waiting for you to connect. When you ask for a connection, DSQL will simply pop one of these QPs out of the pool, and your application can start to run transactions. Now, let's look at failure of connections. We've got 6 connections open, one of them has failed. Ideally, what's happened here from an RTO point of view is that we've simply experienced an error on 1/6 of our connections. The other 5 connections are totally healthy, right? This is a system with no single point of failure. And what your application needs to do to handle this is to detect that failure, to retry. This is where that retry handler from the optimistic control section is going to come in handy. Add a retry on connection errors, and you'll get another connection, and you're back to 100% availability. Now, unlike failures of storage and failures of the adjudicator, we can't have your application automatically reconnect, right? This is something that you need to do. And so in order to take advantage of DSQL, you need to build the ability to detect failures, to retry on new connections into your application. We were actually quite worried that customers wouldn't realize this because we see page 43 in the manual. And so what we did instead is we said that connections have a 1-hour maximum lifetime in DSQL. And then if you simply use the best practice of a client-side connection pooling library, this is the Java C3PO library, and configure it to do health checks, configure it to have a maximum connection age, then right out of the box, your application is going to be following our best practices. Now, while we do recommend using client-side connection pooling, in DSQL, there's no need to use server-side connection pooling. You don't need PG Bouncer. You don't need RDS proxy. And that's because the QP layer is a separate service, it's horizontally scalable, and so we've been able to build the concept of connection pooling right into the service. So if you want to run PG Bouncer, feel free to do so, but that's just going to be something that you have to manage, patch, monitor for availability. It's not going to provide you any benefits. Now, throughout this talk, I've been showing your application talking to QPs in the same zone. And the reason we do that is to lower latency, right? Postgres transactions that are interactive, you're going back and forth between your client and the application all the time. Each of these trips is going to take some time. And so by talking to a QP in the same zone and to a storage host in the same zone, we're going to give you the best performance. Now, in the event that your application is somehow available and yet DSQL is completely down in a region, don't worry about that. DSQL from the top to the bottom is able to automatically fail over to a healthy zone. And so if an entire zone becomes unavailable, just reconnect and you'll get a healthy QP. If you'd like to learn more about this part of the service, please join me tomorrow at 1 p.m. for DAT439, where I'm going to be doing a deep dive into how we built this. Let's talk about regional failures. DSQL allows you to set up what we call a multi-region cluster, and the way you do this is you create a cluster in region A, a cluster in region B, and then you designate a third region as the witness region. Now you'll notice the witness region doesn't have any storage boxes, it doesn't have any QPs in it, it doesn't have your application in it. The job of the witness region is simply to have a copy of the journal for reasons that we'll get to in a moment. Once you do this, DSQL is going to peer these journals together using a quorum-based protocol, and then our application can continue to be active even across regions. So here you can see we have our application in region A, AZ2, our application in region B, AZ2, and they're both able to do writes. So what happens if region B fails? Well, imagine for a moment that we did not have the witness region. It would be very difficult to disambiguate between region B having failed completely versus region A and region B simply not being able to talk to each other. And this is where the witness region is going to come in handy, because it's going to vote alongside region A to kick B out of the quorum. And DSQL is going to be able to detect this automatically. It's going to reconfigure the journal so that only A and C talk to each other. And if you were somehow able to connect to the cluster in region B, it would be completely unavailable for reads and writes. This happens automatically, again, without any intervention. It happens very quickly. And by doing this, you can continue to use your cluster in region A. There is never any data loss. And if you continue to write data into region A, DSQL upholds its guarantee that transactions are replicated to at least one other AWS region before acknowledging the commit. Meanwhile, later, region B is going to come back online. DSQL will detect that, it will catch it up to date, and then it will undo that configuration option and we'll be back to 2 zones. So how do you take advantage of this? The pattern we recommend is the same one that we've been using throughout this talk, one of active redundancy. And so you should deploy your application alongside the cluster in region A and alongside the cluster in region B. And there's a couple of reasons for this. One reason is that you're going to get the best performance, right? Because again, you have this low latency connection to your cluster. But the second reason is this is going to allow you to continuously validate that your application works in both regions. On top of this setup, you should create some kind of global endpoint. You can do this with something like a Route 53 DNS record. And then you automatically direct your customer's traffic to the closest available healthy region. So what happens if something goes wrong, region B goes offline? You're not going to lose any data, and DNS is going to start to shift your customers over to the healthy region. And you know that this region is going to be healthy. Why? Because you've been exercising it all of the time. So this is my favorite slide I had to make here throughout reInvent because there's not a lot on it. And the reason for that is with DSQL, there's simply no maintenance for you to worry about as a customer in the same way that there's no maintenance to worry about as an S3 customer. DSQL is a fully managed service. Our active architecture is allowing us to do much more maintenance on your behalf. So think about those query processes, right? They're only running for an hour. After an hour, either you hang up or we hang up, we throw them away, we make a new one, and that new one is going to have the latest operating system, the latest security patches, the latest performance improvements, the latest features, and so there's just really nothing for you to do as a customer. Okay, so what are the takeaways for today? Aurora has 3 engines. We have Aurora for Postgres, for MySQL, and our newest engine, DSQL. Out of the box, all 3 of these engines are going to give you 3 AZ durability. Both of these, out of the box, all 3 of these engines are going to give you the ability to scale your workloads. With APG and AMS, you're going to scale primarily by going up for writes and out for reads. With DSQL, we offer hands-free automatic scaling, but you need to make sure your application and schema are designed to work best with the DSQL architecture. If you've outgrown a single region, consider going multi-region. With APG and AMS, you can test your failover practices without losing any data. And with DSQL, you can take advantage of active-active across regions. And finally, all 3 engines offer easy maintenance with automated security updates and minor version upgrades. Thank you so much for attending our talk. Tim and I will be hanging around afterwards for questions, so please do come and talk to us. And thank you. Have a great re:Invent. Please complete the session survey in the mobile app.